Hello. Now we'll be seeing the work cell design and control. So after fabricating the robot, how industry will design the work, okay? How where to put the robot and so that the maximum efficiency can be achieved. So if you look at this, so robot cell design layout. So we'll this slides will have a robot cell design layout and multiple robots where to put and machine interface and so what is the consideration we are while we are designing the work cell design, then interlocks, error reduction and recovery, robot cycle analysis. So this we'll see it now. So, company, if you want to implement the robotics, so what we have to do first, the program and its operation. So they must be familiarized with what is the type of program because each robot company they are having their own language. Okay, suppose if you are taking ABB, they are having a rapid traverse language. So the own language they are having it. So we must know how they are doing it and plan survey. So what where to implement, see we cannot just like that we cannot buy a robot and then we cannot implement it in the real time scenario. Instead of that we have to identify the term is called return of interest, ROI. So whatever the investment we are putting it, whether we are getting a return back or not, that we should identify. So we have to apply the selection of application and selection of the type of robot, what type of robot, because we cannot suppose the application requires a 3-axis robot alone, but we need not go for a 6-axis. This is a costly, little bit costly, no? So that we need not go. So selection of application and selection of robot is very important, and we have to do a detailed economic analysis and capital authorization. And if you look at the robot cell layout, the three types of layouts are available: robot centered work cell, inline robot cell, mobile work cell. So three type of one we'll see one by one. So center of work cell. So now the robot center work cell. So we will have the incoming material will be coming here, and machine 1 and machine 2 the process and then outgoing material. So this robot is placed at the center. Okay. So options are two or three options are. One is by taking the suppose the incoming materials coming in a conveyor, the robot can pick it up and place it at the required location in the machine 1. After processing it out, it will come to this end. So the robot can pick it up and place it to the required location in the machine 2. So after processing it out, it can come here. So the robot can pick up the third this point, then it can go to the outgoing. Suppose if it's outgoing materials as a conveyor, it can go it. Okay. So if you look at the this robot is having a input layer, it is coming here, an output layer. So the processing on machine, the robot can pick up the one machine layer 1, and it after processing it out, it can go to the machine 2, and after processing the machine 2, it can go to the machine 3. So one single robot can utilize the multiple operations so that the cost of the production will be less. Now inline robot, suppose the work parts are coming, so you need a very high operation or you need a unique robot which you want to control it. Okay, so especially suppose the work parts are coming here, you have a say welding robot. Welding robots doing the particular object in the welding here, and then the part after completing the robot by one, it is processed to the next location where robot 2 can be processed it, and it can go to the third location where robot 3 can be processed it. So if you look at here, the line, it is like a line. Okay, it's a line, it's a serial like a belt conveyor. All the components are coming in a lined manner and robots are placed. See, three robots are placed such a way that they are picking the component, processing it, and then performing the next one. Okay, so here instead of picking one, the robot can do a welding, soldering, brazing, or whatever required, or any other simple operations can be done. Now there is a welding robot, how it can be done. See, Here almost all car manufacturing like this layout will be there. The robots are placed here. This robot end effector will be coming here and doing the required operation. This end effector will come here and doing the required operation. This end effector will come here and do the required operation. This end effector will come. So at a time, 4 robots are used to manufacture a single component, so that production time will be reduced. So here if you look at the another type of layout where hangover one, see that is, 4 robots are placed in the ground floor and 2 robots are placed in the above one, that is a partition. So it can do in the kangaroo manner also. Okay, this is also one of the type. So the robot can be used intermediate transfer, continuous transfer, non-synchronous transfer. So if you want intermediate means middle, not the continuous one, is a limited time it can be used, and continuous transfer means continually it can be doing it, and non-synchronous means without any sequence also it can perform. Now we'll see what is intermediate transfer system. The parts moved in a start and stop motion from one station to another one along the line. It is also called synchronous transfer line, since all the parts are moved simultaneously to the next stop. See, suppose 5 components are coming. Assuming that the processing by a one robot welding is taking place at 5 locations one by one, then all 5 components will be placed to the next location, okay, at a time. So that is called intermediate transfer. The advantage of this system is that the parts are resisted in the fixed location and orientation with respect to the robot during the part work cycle. And if you look at the continuous transfer system, the work parts are moved continuously along the line at constant speed. See, the robot has to perform the task for the part moving. So here, the robot, the part is not a stationary one. So it will be moving in a conveyor. Conveyor, say, if it is a 10 meters per second, the speed is given as a 10 meters per second. When it is reaching a required location, the operation has to be carried out by a robot, and it has to move to the another location, say 10 meters per second. So continuously the parts are moving. Accordingly, the robot has to perform. The position and orientation robot with respect to any fixed location are continuously changing it. So there will not be any fixed one. It is continuously changing it. So this results tracking the problem, that is robot must maintain a relative position and orientation of the tool with respect to the work part. So the robot should not be fixed one. The robot also has to identify each one while it is, because the parts are moving. So we must identify where the parts, accordingly the robot has to work. The tracking problem can be particularly solved by moving the baseline and tracking system by moving the robot parallel to the conveyor at the same speed, or by stationary baseline tracking system, or by, that is, computing adjusting the robot to the tool to maintain the position and orientation with respect to moving part. See, the robot usually traditionally the robot will be placed as a stationary one. So instead of a stationary one, the robot the same speed. Suppose assuming that you have a rail, the rails are coming in a one, and if you are running the rails, following the rails in the same speed, when the relative motion is keeping as the same, it is considered as a stationary one. So it can do the welding required operation, and the coordinate problem will not be erased. So that is the one it is given here. So you can look at here how it can be done. So this is the tracking system, how this is the continuous one, where the robot from here to here, how it is done. So secondary tracking involves considering engineering problem. First, the robot must have sufficient computational and controlling capability. So it must be an advanced robot. And secondly, the robot tracking window must be adequate. So it has to adequate about the where the parts and everything is available. Third, sensor system to identify the different parts coming to the tracking window, also tracking the moving parts with the robot tool. So where the robot has to identify where the parts are there, where to do a required operation, so that it will not do any mistake. Otherwise, the part will be moving from the one location to another location. While reaching the robot to the required location, by the necessary part will not be done. So that is the another problem with this method. So non-synchronous transfer system. So this is the power and free system where each work part moves independently with the other parts and stop and go manner. So there nothing that is a relative motion between the two workpiece and robot. Okay, it's not existed. When the workstation has finished the working on the work part, that part has been proceed to the next station. Hence, some parts are being processed on the line at the same time that the other being transported located to the between the station. So here the timing varies according to the cycle time required by each station. So here we suppose we have say one location, two location, three location. One location the components are processed, and when it is moving to the second location, the second robot will do the performing operation. So that it will calculate the between the time between the first location to the second location, and what operation, which place it has to be carried out, that will be taken care of. And the design and operation of this type of transfer system is more complicated than the other two, because each boss must be provided with its own independently operate moving cart. So each part will be moving in a separate cart. That is, cart means moving platform. So it should have a separate belt conveyor system or any other guided vehicle system. It has to go it. Okay. And however, the problem of designing and controlling the robot system used in power and free method is less complicated than the continuous transfer system. Non-synchronous, for the irregular timing of arrival, sensor must be provided to indicate the robot when they begin its work cycle. The complex of the problem of the particular registration with respect to the robot must be solved in the continuously moving the conveyor system and not encounter on the either intermediate or non-synchronous system. So from one location to another location, robot has to be given a one. So just like a proximity sensor, it has to, once it is reaching the particular sensor, that sensor has to be activated, that signal has to be given to the robot. So second robot will be performing the operation, so that error will not be occurred. Okay, error will not be occurred. So mobile robot system. So this robot system, if you look at here, the robot system, it will have a track. This is the track where the robot is not a stationary one. It will move it out from here to here and performing the operation the machine 1 and machine 2. So this arrangement, robot is provided means of a transport which is such as a mobile base with the workcell to perform the various tasks at a different location. So because see, some components of machines will be very big and it cannot be moved. Okay, it cannot be, the components will not be moved, and it will be very rigid. So at that time you can go with a small mobile robot where the weight of the mobile robot can be less, so it can move from one location to another location. Okay, through the tracking mechanism. Then the operation can be, so the overall cost of the robot or overall the layout cost will be less. So the mobile robot works well suitable for installation where the robot must be serviced more than one station. So the production machine that goes along with the processing cycle. The station cannot be arranged in the robot in the robot cell arrangement. So this type of robot cell arrangement is not possible. It can go to the linear type. Now mobile example, we'll see it how it is done. So here see, like a cantilever beam, overhaul beam, the mobile robots are moving. This is the robot. Okay, this is a robot. So machine 1, it is processing it out, and machine 2 and go on. So from the input 1, depending upon the requirement, it can perform the operation. Here the whatever the end effector which is placed at the here, so that will perform the at the machine 1 and machine 2 and the required input and output layer. So this hanging layer will be placed. So multiple robot machine interface. So how to do a machine interface? Okay, physical interference of the robot and machine interference. So two things, machine interference. So one machine after performing it, it has to go to the next operation, because one specific operation will be done by a single machine. And similarly, the robots, if you are using multiple robots, that should not interfere with the machine or another robot also, it should not interference. So however, the robot, there are cases where the robot work on the same component piece where The robot in turn work on the component. See, some cases the robot will be which is placed in such a way that it is not interference with the machine, okay, but when there not be risk of collision, we can follow this method. So machine interference, what is machine interference? This occurs when two or more machines are being serviced by one robot. So when the robot is serviced by say robot center layout, which we have seen it, one robot is performing with the two or three robots. At the time, the machine interference should not be occur. So the machining cycle are timed in such a way that the ideal time is experienced by one or more machines. While one machine is being serviced by a robot, the machine interference can be measured by the total ideal time of the machine in all the cells compared to the operator or cycle time. The measure is commonly expressed as a percentage. So here, after performing operation in one machine, okay, and the ideal time, see, if you are having a say 5 operations has to be carried out, after performing one operation, the machine can go with the ideal time. At the same time, the second machine can do the operation. Otherwise, the ideal time, suppose one component is completed, then it can perform with the second operation. The robot can pick it up and place it in the second machine. At that time, the machine one has to be an ideal one, so that it cannot do the collide version. So that is the one it is going. So this is expressed in terms of a percentage. So now it's giving a sample calculation how to do it. So if you look at here, a 3 machine cell in which robot is used to load and unload the machines. Okay, robot is performed to load or unload the machine. Each of 3 machines are identical with the identical cycle time of 50 seconds. So each robot is having identical, each machine is having identical one, and cycle time is 50 seconds. This cycle time divided by the number of run time, 30 seconds, and service time, load and unload, is 20 seconds. So the split up of 50 seconds, the machining time. So the machining time which they are doing it out, real machining time, it is 30 seconds. Loading into the machine by a robot, it is unloading. So say 10-10, okay, 10-10. So that is a split up. The organization wants cycle time is shown in the robot and machines are given below. So it can be seen that each machine ideal during its 10 seconds, the robot is fully occupied. So now we will see what it is happening. So the robot 1, when it is loading to the 20 seconds, it is taking the load, okay, 20-second machine is taking the load. Machine 2 is ideal and machine 3 is also ideal. When the robot is taking the load 2, it is loading to the second operation. At that time also machine 3 is free. When the load is taking the third load, it is correspondingly going to the machine 3. At that time, machine 1 and machine 2 are performing the operation, running the operation. After 60 seconds, the machine load 2, after taking the load 1, the fourth load, it is going to the machine 1. At that time, another 2 machines are free. And load 2, it is going to the 1. So if you look at this chart, when the load is happening, others are not doing. See, initially when it is loading, because the parts are not placed here, so it will be ideal one. And when suppose if you are here also should be an ideal one, because running should not be, because when the components are placed in the third component, it can run it. Okay, run means it can perform the operation. So similarly here also, when the load is happening, another up to the load it's happening, because only one robot we are using it. At that time, second machine can perform the operation and third machine also perform the operation, such a way that we should identify what is the total. So total identity of 3 machine is 3 into 10 seconds, so 30 seconds. Okay, so totally it is 30 seconds, it is ideal. The cycle time of a robot is 3 into 20. So the cycle time, so while the processing with the machine, because the machining time is 30 seconds and loading unloading is 20 seconds, there is a 10 seconds gap. So that 3 in 20 seconds, so if by calculating this gap, we can calculate 60 seconds. Therefore machine interference is 30 by 60, so 50% chance of machine interference. So like that we have to calculate the machine interference for each one. Without doing, if you are not doing properly machine interference, the robot will collide to each other. So that should be avoided. Okay. That is not a desirable one. So by the requirement of the one, we have to do the calculation. Thank you.